The final speaker of this session is Ms. Minghan Du. Her title presentation is Study of Objective Parameters of 3D Visual Fatigue based on Analysis of Salient Area. Ms. Minghan Du is a graduate student in the School of Optoelectronics at the Beijing Institute of Technology.
Hello, everybody. I'm Minghan Du from Beijing Institute of Technology. And today, the title of my presentation is The Study of Objective Parameters of 3D Visual Fatigue based on Analysis of Salient Area. So the aim of our study is to analyze how salient area of 3D images influence visual fatigue. So we performed a comparative experiment to measure the visual fatigue when watching 3D images with different salient area by analyzing ECG signals and eye tracker data. And here in the rest of my presentation, I will give more explanations from these 5 parts. The first is the 3D display and visual fatigue, and the second part is saliency detection. Then I will introduce our experiment design and some results. Finally is our conclusions and introduce some of our future work. So the 3D display has expanded into many domains like education, medical care, entertainment, architecture, and so on because of its stereoscopic perceptions. However, the users of 3D display will suffer from discomfortable symptoms like headache, nausea, and other symptoms which also called the visual fatigue. So visual fatigue is caused mainly by conflict between convergence and accommodation. Here we can see in the figure A, when we are watching an object in real world, the vergence distance and the focal distance are same. But in figure B, when we are watching an object in 3D environment, the vergence distance and the focal distance are different, which can cause the conflict. So it's very necessary to evaluate the visual fatigue. In existing studies, there are 2 main measurements. One is subjective measurement, and the other is objective measurements. In subjective measurements, it contains the psychophysical scaling, questionnaire, and others. And for objective measurements, it may depend on the theory of fatigue. So it evaluates the visual fatigue based on the physiological signals like EEG, EOG, ECG, and eye movements. Here in our studies, I use both subjective measurements and objective measurements, where I may refer to the questionnaire, ECG signals, and eye movements. So here I will introduce some information about the saliency detection. When we are watching a scene, we will shift our gaze to select a sight of the most salient object first. So saliency detection is one branch of visual attention, which has served as a pre-processing procedure for many vision tasks. With a large amount of visual information, the visual attention would selectively process the important part by filtering out others to reduce the complexity of scene analysis. This important visual information is also termed as salient regions or regions of interest in natural images. Here in the first row, we can see there are some original images with a simple scene. And in this situation, it can more easier to detect the salient object. Well, but in this situation, in the first row, there are some original images with complex scene. So we can see in the ground truth, it can detect more than one salient object. So in this this situation, sometimes we can use the eye tracker, like the third row show. Well, the region in the yellow frame means this part is more salient. So to detect the saliency more effectively, the methods are mainly based on these 2 approaches. One is bottom-up, and the other is top-down. The bottom-up is data-driven and task-independent. It is a perception process for automatic salient region selection for natural scenes. And the top-down is a task-dependent cognitive processing affected by the performed tasks, feature distribution of targets, and others. So based on these 2 visual attention mechanisms, there are many saliency detection method. In this figure, it shows a simple process of how to calculate the saliency map. The input image is first decomposed into a set of topographically featured maps, like colors, intensity, orientation, and others. The different spatial locations then compete for saliency within each map. All feature maps feed in a purely bottom-up manner into a master saliency map, which topographically codes for local salient over the entire visual scene. So that's all about the saliency detection information, and then I will introduce more details about our experiment. As the figure shown is our experiment environment. Here we use an LG 3D TV to display our 3D images. And the eye tracker was used to record the eye movements, and the ECG signals were recorded by BioPack MP150. CO2 other computers were used to control the ECG signals and the eye tracking data collection process. Well, 12 subjects from Beijing Institute of Technology participated in our experiment with an average age 24.6 years old. And the visual acuity of all subjects is qualified. During the entire experiment, every subject's eye tracking data and ECG signals had been recorded, and the data from all subjects were used in the analysis work. So here I will introduce some details about our stimulus. Here we collect 108 3D images from the existing datasets and the 3D images website. And the content of stimulus concludes the indoor and outdoor environment, and the salient objects in the images contain humans, animals, plants, and others. In this figure, the value in the figure means the number of images in different tabs. For example, the red part means the image with a background is forest and no salient object. There are 26 images, and the dark blue part means there is no images in these tabs. So to conduct the comparative experiment, we divided these images into two categories. One group are images with salient area, and another group are images without salient area. So we make these categories mainly depend on the saliency maps of all these images. So the images we use here were calculated by a novel saliency detection method. Well, this figure shows all images with salient area and their corresponding saliency maps. And this figure contains all images without salient area and their corresponding saliency maps. Well, however, because the limitations of the saliency detection method, for some images, their saliency maps are not look very good. And this is our procedure. So before the formal watching task, we have to calibrate our eye tracker. And in our experiment, there contains the 3 groups. For each group, there are 4 subjects and 3 sections. In group 1, its watching order is S1 to S3, and which S1 to S3 are 3 sections, and which contains images with salient area. And in group 2, the watching order is US1 to US3, and there are images without salient area. And a random group just watch images in a random sequence. So in each section, there contains 18 images, which means for each subject, he or she have to watch 54 images totally. And of course, meanwhile, after each section, the subjects need to finish a 10-level skill questionnaire to mark their subjective feeling. So that's all about our experiment design. Here are some results. First, this is the subjective results. Here, one-way ANOVA test was adopted, and the significance for all subjects' subjective data is far less than 0.05, so which means there is a significant difference. In this figure, we can see the entire trend is rising except the group 2, which is the red line. It decreased after the second part. And here are the objective results. Here we use the AOI contrast results. This is calculated just by the eye tracker. And for each image's patches, whose mean gaze time is more than 500 milliseconds and 400 milliseconds were found respectively, and calculated the max value and the sum of time for each image. So we can see in the figure, the mean gaze time of images with salient area is higher than images without salient area in all situations. Here we do this calculation just to prove our category's rationality. And these are the eye tracker results. We can see from the first figure, the blink frequency of group 1, which is the right line, is lower than other groups. So it illustrates that the visual fatigue in group 1 is more severe than that of the other two groups because of a decreased blink frequency means the rising fatigue. However, from the other two figures, we can't see any obvious trend to make some help to the problem. Well, this for ECG signals, it contains two parts. The first part is the frequency domain. The human sympathetic activity will be more active with an increasing visual fatigue, which causes the low frequency to rise and the high frequency to fall. So these figures show the frequency domain results. We can see the second figure is the high frequency domain. So group 1, which is the red line, is lower than other groups. So it can be illustrated that the group 1 visual fatigue is more severe. Well, still for other parameters, there is also no obvious trend. And in time domain, the mean heart rate, standard difference heart rate, and approximate entropy have a positive proportional relation with visual fatigue. We can see in these figures. In time domain, almost all parameters can show an obvious trend that the group 1's visual fatigue is more severe than other groups. So these are about the results. From these results, we have some conclusions. The subjective result shows an obvious trend that subjects suffer from visual fatigue after the experiment. Well, our objective results consist of the analysis of 3 eye tracking parameters and 9 ECG parameters. According to analytical results of the blink frequency and ECG parameters, subjects in group 1 are more easily to have visual fatigue or have a more severe visual fatigue. So it is preliminarily inferred that users who watch 3D images with salient error may suffer from a more severe visual fatigue. Well, that's all about the conclusions. However, there are still many problems in our experiment, like the experiment duration and task design are potential influential impact factors. And in our experiment, the depth of the stereoscopic images is not unified. So when we are analyzing the relationship between salient error and visual fatigue, there might be the influence from depth difference. And in this experiment, we estimate the salience based on low-level features such as color, shape, and edge. And the salience based on such high-level features as semantic ones are not considered. Our watching task is free viewing. Although our eye tracker can have a record for subjects' eye movements, we still can't ensure that every subject's eyesight always concentrates on the images. So all these problems will be resolved in our future work. So that's all about my presentation. Thank you for your attention.
Thank you.